Okay, let's talk about heat and calorimetry. So first, heat. Heat we symbolize using the letter Q. And heat is the energy that's transferred between two objects because of a temperature difference. You can actually have heat transferred when there's a phase transition for a substance, and in that case, there isn't actually a temperature difference. Also, you can have heat transferred when a chemical reaction occurs, and that isn't, a reaction doesn't occur because there's a temperature difference between, say, the reactants, but it can cause there to be a temperature change in the surroundings. And so we'll look at how a temperature difference can be associated with heat. Okay, but basically, if you are focused on things having different temperatures and as a result heat being transferred or energy being transferred, which that transfer we call heat, then it's always going to happen such that the energy is going from the hotter object to the colder object. Okay, and that happens until they reach thermal equilibrium, meaning until they reach the same temperature. Now, there is a quantity that we can relate to heat that helps us tie it together with temperature change, and that's the specific heat, which we symbolize as a capital C. Sometimes specific heat is also called heat capacity, so that's good to know as well. So I probably use the term heat capacity even more than specific heat. Heat capacity can be in different units, but a specific heat is the amount of heat that you need to add to something per gram to raise its temperature by a degree C. Okay, whereas you can have like molar heat capacities where it's on a per mole basis. And so it just depends on the unit if someone starts to specify the term a little bit different, or possibly the conditions. But specific heat capacity, it's all pretty much the same thing. And I'll use a capital C. Some resources you'll see it's a lowercase c or possibly an S, or there's subscripts on the C. But you don't need to worry about that. You can use a C for heat capacity or specific heat. So we can relate that to the actual amount of heat. We can use a heat capacity to quantify the heat for a given temperature change. And to do that, we'd use the equation Q equals mc delta T. And in this, Q is heat, M is mass, C is your heat capacity, and delta T is our change in temperature. And you can rewrite that if you want as TF minus TI. So the final temperature minus the initial is the change in temperature. Okay. The one nice thing about this equation having a change in temperature is that you can plug in the temperatures in Celsius or Kelvin. Okay. Either will give you the same change in temperature, just as long as you plug them both in the same unit. Okay, and so then you also will see your specific heats or heat capacities. Their units will be usually something like joules per gram degrees C. Sometimes you'll also see it written as joules per gram Kelvin. And it doesn't matter if they say it's per degree C or per Kelvin, those would be equivalent values because it's related to a change in temperature. Okay, so when you use this equation, what you should see is that sometimes Q is going to come out positive and sometimes it's going to come out negative. It comes out positive when heat is being absorbed, okay, or gained. It comes out negative when heat is released. And really that sign difference is due to the delta T term. okay? Because M, or mass, that can only be a positive value. You can't have a negative mass. Same with the specific heat. The specific heat is always a positive value. So the only thing that can be negative, causing the Q to be negative, is the delta T, okay? And the sign of delta T is all based on, is your temperature going up or down? If the temperature is going up, TF is higher, so delta T is positive, okay? Meaning heat is absorbed. Well, if something absorbs heat, its temperature goes up. That should make sense. If the temperature goes down, meaning your final is smaller, then you take a smaller number minus a bigger one, you get a negative value, okay? And so if that were the case, if temperature went down, that would be because heat is being released. And so this equation will give you a negative value for Q case. Okay, so the sign is just indicating the direction of this energy, okay, where the energy is going. There isn't really such a thing as a negative energy. Okay, so that sign is just helping us understand where it's going. Okay, now specific heats, it's good to know that those are known values. You can look up tabulated values of specific heats for substances. It is specific to the substance. So if you have a different substance, it's going to have a different specific heat, okay? Even if it is in a different phase, okay? So you can see different specific heats for different substances in this table. They even give them to you in joules and in calories. But you can also see, like for the water, they give you solid water, so ice. They give you liquid water, and they give you gaseous water, which is steam. And those all have different specific heat values, okay? So your specific heat is specific to the substance, but also the phase, okay? So you can look up those values if they're not given. This is just a table that you could use as a resource. Let's do some examples. So this first one says how much heat is required to increase the temperature of 21.3 grams of aluminum from 5.00 degrees C to 38.2 degrees C. And I give you the specific heat as 0.897 joules per gram degrees C. So I'm just going to rewrite these values and label them. So we have a mass, it's 21.3 grams. We have an initial temperature of 5.00 degrees C. We have a final temperature of 38.2 degrees C. And we have a heat capacity of 0.897 joules per gram degrees C. And we want to know how much heat is required to cause this temperature change, okay? And so it's good to write down that equation. Q equals M C delta T, okay? Or we can rewrite it as Q equals M C times TF minus TI, okay? And then I can just plug in the information. So Q equals 21.3 grams times 0.897 joules per gram degrees C times 38.2 degrees C minus 5.00 degrees C. Okay, now first we need to do that subtraction, so 21.3 grams times 0.897 joules per gram degrees C. And then let's see, 38.2 minus 5.00 gives us 33.2 degrees C, which I should have done in my head, but that's okay. Then we've got 21.3 times 0.897 times 33.2 And we're going to round that to 3 sig figs because that's the fewest we have in our multiplication step. So 634 joules. Okay. And that is because, let's see, grams cancel and degrees C cancels. Okay. Sure, I typed that in. Yeah, that's right. Okay. Okay, so 634 joules of heat was absorbed in order to cause this temperature change. Okay, let's do another one. Here it says, what is the final temperature of water when 275 grams, so I'm just listing my information as I get it, of water at 21.5 degrees C, so that's my initial, is heated with 15.8 kilojoules. Okay, and so we want to know the final temperature. We also have the heat capacity for 184 joules per gram degree C. Okay, sorry, that's very, very sloppy. Rewrite that. So C equals 4.184 joules per gram degree C. Okay, and we want the TF. And so we can use the equation Q equals MC times TF minus TI. Now you can plug in the values and then rearrange, or you can rearrange first. Let me just rearrange it first. I'm going to divide the MC over, so it would be Q over MC equals TF minus TI. And then I'm going to add the TI over to get TF. So TF would be equal to Q over MC plus TI. Okay, and so then I'm just going to plug in. So TF equals my Q, which was 15.8 kilojoules, over my mass of 275 grams times the heat capacity, 4.184 joules per gram degree C, and then plus the 21.5 degrees C. Okay. So now the first part we should do is do all our multiplication, division, and the fraction. But pay attention to the units. So here we've got kilojoules on top and joules on bottom. That's not going to work. Those don't cancel. So I'm actually going to add in conversion to get rid of the kilojoules on top and make it into joules. Okay. If you'd prefer, you can do this off to the side and then just plug the joules into the equation. But 1 kilojoule is 1,000 joules. So that's going to cancel the kilojoules part. It's going to cancel the joules from the bottom. Grams cancel, and we're left with degrees C on the bottom of the bottom, meaning our answer to that fraction is going to end up being in degrees C. So I'm going to take 15.8, I'm going to multiply it by 1,000, then I'm going to divide it by 275, I'm going to divide it by 4.1. So that gives me, so 3 sig figs, 13.7 degrees C, which needs to be added to 21.5 degrees C. And it should be rounded to 1 decimal, so it should be 35.2 degrees C is the answer. So that would be our final temperature when we heat that sample of water with the 15.8 kilojoules. Okay, now let's talk about calorimetry. This tends to be something that scares people. It sounds like a scary word, it sounds confusing, but really this is just the experimental technique that we use to quantify heat. Okay, So we use it to quantify the heat associated with something in kind of an indirect way, okay? Um, and you can even use it to quantify other things associated with heats, like heat capacities or what the temperature is going to end up being. But in general, we use it to quantify heats. And so we do this to quantify the heat associated with some object or most often a chemical reaction, actually. Um, and so what we do is we observe the surroundings and then we relate that to the system, okay? So the surroundings, we monitor a temperature change because that's very easy to do. We just use a thermometer and see, does the temperature of the surroundings go up or down? And then that tells us about the heat of the surroundings, which then is related to our system. So when we use that term system, we're talking about whatever object we're trying to study or whatever reaction we're trying to study, okay? And so what you need to realize is those have to be directly related. The energies of them have to be related. Where the heat of the system and surroundings have to be equal in magnitude but have an opposite sign. Meaning if the system is losing heat, meaning it's releasing heat, where that is going is to the surroundings. So the surroundings are absorbing that heat, okay? And so the magnitudes are equal, the signs are different because the direction it's going is opposite, okay? Same with if the system gained heat, that has to come from somewhere. That would be coming from the surroundings, okay? And the surroundings thereby would be losing it. So really, this is just applying the conservation of energy, okay? And so in reality, we're kind of doing this in some contained system where one thing we're focused on and we're monitoring what surrounds it in that kind of container. And then we're relating the two. And so in this, you can write this in an equation form. You could say the Q of the system is equal to the negative Q of the surroundings. Okay. Another way sometimes this is written is Q hot equals negative Q cold. Okay, so that would be, you know, if we're definitely talking about just taking this hot object and putting it in this cool surroundings, or we're taking this cold object and putting it in this hot surroundings, okay? Their heat, you know, the heat associated with the temperature change that ends up occurring are equal, but have an opposite sign, okay? And so saying Q of system equals negative Q of surroundings is the more kind of generic way to say that. Now, you can also, you know, replace system as an object or a reaction, okay? And so all of those equations really are the exact same thing. It's just applying the conservation of energy, okay? So we're going to look at a few examples that are focused on kind of the hot object, cold object scenario. But it would be the same type of process if it was a reaction. You would monitor the temperature change of the surroundings, calculate the heat, and then that is the heat of the reaction or whatever your system is. Okay, it just has an opposite sign. It's just doing the opposite thing with it. So let's look at an example where we have copper. It's initially at 50 degrees C. It's put into 100 grams of water at an initial temperature of 19.50 degrees C. And the final temperature of the copper in the water at thermal equilibrium is 20.20 C. And then I give you the heat capacities, okay? And these are both actually specific heat capacities. I don't know why the one I accidentally labeled CP, it's really a CS. And so we're not looking at the complexities of heat capacities right now. We're just looking at regular heat capacities. So we don't need to worry so much about that notation. But I give you 3 questions here. It's kind of to walk you through what's going on. So the first question says, how much heat is gained by the water? Okay, and so to calculate that, we could set up an equation and say, okay, well, the Q of water should be equal to the mass of water times the heat capacity of water times the change in temperature of water. Okay, and so we should have that information that we can plug in. Okay, so we have Q water. Actually, let me just continue this equation instead. Let's just say equals, and then plug in the mass of water, so 100.0 grams. Okay. And then the heat capacity is 4.184 joules per gram degrees C. And then the change in temperature, my final is 20.20 degrees C minus my initial of water was 19.50 degrees C. Okay, so I'm going to do that subtraction first. So I'm just going to carry down the 100.0 grams and the 4.184 joules per gram degrees C. And 20.20 minus 19.50 should give me 0.70 degrees C. Okay. And then I'm going to multiply this. So I'm going to take 100 times 4.184 times 0.7. That gives me 292.88 joules, because the grams cancel and the degrees C cancel. But that should be rounded to 2 sig figs because that change in temperature is only 2 sig figs. So really the answer is 290 joules. Okay, that's the heat that is gained by the water. Now the next question says how much heat is lost by the copper. Okay, now you might initially think, okay, I'm going to take Q of copper equals mass of copper times heat capacity of copper times change in temperature of copper. But right away, you should see there's a problem with that because you're not given the mass of the copper, right? So you can't use that equation. That's not going to work, okay? But this is a thermal equilibrium problem. You have a hot object put into cool surroundings and heat is transferred till they equilibrate in temperature. And we already calculated how much heat the water gained. So that must be equal to the heat that copper loses, okay? So the heat of the copper must be equal to the opposite sign of the Q of the water, meaning our answer here is negative 290 joules, okay? Now the next question asks, what's the mass of the copper, okay? So now we can actually use this equation. We have the Q of copper. The Q of copper is 290 joules, or negative 290 joules. And we want the mass of copper. And we have the heat capacity, 0.385 joules per gram degrees C. And the change in temperatures, 50.00 degrees C minus 1. No, that's backwards. If I plug it in backwards, that's going to really mess up my signs here. So it should be final temperature 20.20 degrees C minus 50.00 degrees C. Putting the temperatures in the right place does matter. So 290 joules. So I'm going to do the subtraction first. So I'm just going to carry everything else down. Okay, so my change in temperature comes out to, it should be 29.80 degrees C. And then I could take the negative 290 and I'm going to divide over 0.385 and also divide over the 29.80. And that'll give me my mass, okay? And actually, I messed up here. It's negative 29.80, right? 20.20 minus 50 should be a negative value. So when I divide those things over, I'm going to get a mass that is positive, because you can't have a negative mass. And it needs to be rounded to, let's see, 2 sig figs because of the heat. So 25 grams would be my mass of copper. Okay, let's do a couple more examples of dealing with thermal equilibrium and this heat transfer. Now this one says, what is the final temperature of water when a 10-gram piece of iron at 75 degrees C is placed in 125 grams of water with an initial temperature of 21.5 degrees C? And we have some heat capacities. So with this, since we have these two objects, it's helpful to kind of gather your information based on what you have. So for the water, I've got, let's see, 125 grams. So the mass is 125 grams. Okay. And the iron is 10 grams. And then let's see, the 75 degrees is my initial temperature of my iron. Oops. And then let's see, 125 grams of water with initial temperature, 21.5 degrees C. And then we have the heat capacity. Water is 4.84 per gram degrees C. And the heat capacity of iron is 0.4503 joules per gram degrees C. And we want the final temperature of water. Okay, and so you can set up a Q equation for each one of these. You could say that the Q of H2O is equal to the mass of H2O times the heat capacity of H2O times the TF of H2O minus the TI of H2O, which I just barely had enough room for. Okay. And so we have that equation, but with that equation, we're looking for TF, right? But the problem is we also don't know Q. Okay, but we can set up our equation for iron as well. Let's write that one down. So Q of Fe equals the mass of Fe times the heat capacity, Fe, times the final temperature of Fe minus the initial Fe. Okay. That equation, we don't know Q and we don't know TF. So it makes it look like we've got lots of unknowns and we have a big problem because we're trying to solve for something. And I guess I have the answer down there at the bottom. I'll just move it for a moment. Here we go. So we've got 4 unknowns and only 2 equations. That's a problem. But it's really not a problem because we don't really have 4 unknowns. So you have to remember that we're putting these objects together and they equilibrate in temperature. Okay, and so in reality, your TF of H2O is actually equal to TF of iron. Okay, meaning that that's all the same temperature. Okay, so I'm actually just going to change those out for just simply TF in the equation. The other thing we know is that one thing is going to be losing heat and one is gaining. So your iron's hot, it's going to release heat, and your water is cold, it's going to absorb that same amount of heat. So really, your Q of water is equal to your negative Q of Fe. Or you could say it the other way around. You could put the negative in front of the water if you wanted to. And that means we can actually set those equations equal to one another. and just put a negative sign in there. So that's what I'm going to do. I'm going to take, the Q equation for water and set it equal to the Q equation for Fe and just place a negative sign in there. So I'm going to start with the mass of water. So 125, and actually we've got a ton of stuff written on this slide already, so let me just write in a different color. This is my setup for the calculation. So 125 grams, because that's my mass of water, and then 4.184 joules per gram degrees C. It's my unit for my heat capacity there. And then we have TF, which we are looking for, minus my initial temperature of water, 21.5 degrees C. And so that's the Q of water. Okay, all of that stuff put together is the Q of water, which has to be equal to the negative Q of Fe. And the Q of Fe, or the heat of Fe, is the mass times the heat capacity times the change in temperature. So I'm going to put those things in. The mass of iron, 10 grams, times the heat capacity, 0.4503 joules per gram degrees C, and times TF, which we don't know, minus the TI, which is 75.0 degrees C. Now we have one equation, and there's one unknown. Okay, our one unknown is TF. All we need to do is get those TFs on one side of the equation and solve for the TF. Okay, now I say that's all we need to do. This is actually quite a bit of algebra, so you got to do a lot of rearranging. I'm not going to go through and write out all the rearrangement of this. I'll let you do that. That's just a little bit of an algebra task, but I'll give you the answer. Okay, if you didn't already see it a little bit ago, it should come out to 22.0 degrees C. So you can try that and make sure you get that, but that's how you would set that up. Okay, let's look at one more. Okay, here we've got a question that says you heat 500 milliliters of water to 99 degrees C, and we want to know how many milliliters of cold water, specifically at 12 degrees C, must you add to lower the temperature of the hot water to 35 degrees C. Okay, I give you the heat capacity of water, give you the density of water. So this is kind of like the last one, actually like the last two. You have something hot, you have something cold. This time it is the same substance, okay, but that's okay. Okay, we're still going to set up a Q equals negative Q, but now we're just going to label it as Q hot equals negative Q cold, okay? Or you can say Q cold equals negative Q hot if you want. It's mathematically the same thing. And so these Qs are calculated by taking mass times heat capacity times change in temperature, okay? But we weren't given mass, right? We were given volumes and asked for a volume, okay? But you have to remember density equals mass over volume, right? And so mass is equal to density times volume, okay? So in place of our Q equation, Q equals mc delta T, for the M part, we're going to plug in D times V, because that is mass. So it'd be D times V times C times our delta T, okay? And so we're just substituting this in to here, okay? And we're going to do that for the hot substance, the hot water, and the cold water, okay? And so let's go ahead and set this up. So the density is 1.000 grams per milliliter. Okay, that doesn't matter if we're talking about the hot or cold. Um, although it does change a little bit, we're assuming it stays constant enough. Okay, and then we have 500 milliliters of that hot water, and the heat capacity is 4.184 joules per gram degrees C. And then the change in temperature, 99.0, or no, that's the initial. We always got to do final minus initial, guys. Final is 35.0 degrees C minus 99.0 degrees C. And that needs to be equal to, again, the density, 1.000 grams per milliliter, times, let's see, the volume, which is what we're looking for, right? We want the volume of the cold. And I missed something in my equation, right? I need negative Q cold, so I need a negative sign there. Okay, that's pretty important. That's something that usually people do miss. But if you miss that, your answer is going to come out really crazy. So we got to make sure we have that negative. So heat capacity, and then the change in temperature, finals 35.0 degrees C, minus our initial was 12. So almost kind of ran out of space there. That's okay. Now with this, you can plug in all those numbers and rearrange and solve for volume, but you can kind of simplify this. The density is going to cancel out, okay? Because if you divided it over, cancel out. Same with the heat capacity because it's the same on both sides. Okay, so we can kind of simplify this. So really on the left, we have 500 milliliters times, or actually, oh yeah, we can say 500 milliliters times 35.0 minus 99.0, so negative 64.0 degrees C. And that should be equal to negative volume times that temperature change, 35.0 minus 12.0. So that's 23.0 degrees C. And so now we can just divide over really the negative 23 degrees C and get our volume. So we would take 500 times negative 64 and divide by negative 23. And we're going to round our volume to 3 sig figs, so get 1,390 liters. Okay. Or you could say 1.39 liters if you wanted of water that we would need to add to end up with our final temperature of 35 degrees C. Okay. So hopefully that's enough to kind of get an idea of how you can quantify heat based on a temperature change and how you can do kind of basic calorimetry, how you have information about heat of one thing that you can relate to heat of another that is transferring heat from one thing to another.